Section 4.4, Newton's third law. Sometimes this law is reduced to a simplified form. For every force there is an equal and opposite force, or for every action there is an opposite reaction. In its more complete and accurate statement, if object 1 and object 2 interact, the force F12 exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force F21 exerted by object 2 on object 1. So, for example, in this diagram we have a force from a hammer pushing the nail, but we also have an equal and opposite force from the nail pushing on the hammer. Here we have a pair of objects, perhaps they're interacting with a field force apparently, and the field pulling object 2 towards object 1 exerts the same force as the field pulling object 1 towards object 2. So it should be noted in applying Newton's third law, remember that the action and its reaction force always act on different objects. So back to that book and table example, there's kind of two forces in play here, the gravitational force and the normal force. And there is a gravitational force pushing down on the book, F sub g on the book. And where is its equal and opposite force coming from? There is also a gravitational force from the Earth, force of gravity on the Earth, pulling the Earth towards that book. Same thing with the force of the normal force. We've got a normal force pushing up on the book, force normal on the book. And that's coming from the table. And we've also got a force normal on the table that is acting downward. And I guess there's another situation here. There's a normal force or an applied force, let's call it applied, pushing down from the table on the floor. And there's also a force applied by the floor on the table. So these are the equal and opposite forces. The force downward on the floor, the force upward on the table, the force of gravity on the book, the force of gravity from on the earth from the book, the force pushing up on the book from the table, and the force pushing down on the table from the book. So those are the equal and opposite pairs that the third law of Newton is referring to. When walking, you have a force that is pushing back from your foot to the ground, and as you push from your foot to the ground, the ground in turn pushes forward on your foot. Okay. And that is a frictional force in both directions. The force of your foot on the ground and the pushing backward, and the force of the ground on your foot are both cases of static friction causing you to not slide on the ground. Same thing with a bicycle. The tire pushes backward on the ground, and the ground pushes forward on the tire due to the static friction between the tire and the ground. In a helicopter, the large blade applies sort of a force or a torque counterclockwise, which causes the body of the helicopter to tend to rotate clockwise. And in order to prevent it from rotating clockwise, they have this fan back here that provides a counterclockwise torque to keep the helicopter straight. So a common error in understanding the Newton's third law is to look at this situation and think, oh, for the force of gravity, the normal force is equal and opposite. But those two forces are on the same object. The normal force and the force of gravity here is not an example of Newton's third law. It's two forces applied to the same object. If it is possible for the normal force and the force of gravity to be different, and so the normal force here would be 0 because there's no table there, and the force of gravity would be pulling the monitor down. Again, the equal and opposite force to the normal force here is the force downward on the table. There's the normal force. The opposite of this normal force upward on the monitor is this normal force downward on the table. The equal and opposite of this force of gravity on the monitor is this force of gravity that the monitor is exerting on the Earth. So here is a quick quiz. Imagine a small sports car colliding head-on with a massive truck. The greater impact force acts on A, the car, B, the truck, C, neither. The force is the same on both. So here's our little car, here's our massive truck, and they collide bumper to bumper. At the location of the bumper, which one of these guys is going to experience a larger amount of force? Okay, so the truck exerts the same amount of force on the car as the car exerts on the truck. That's Newton's third law. So the answer is that the forces are equal when they're bumper to bumper. Now there's a lot of good reasons to want to be in the truck instead of that car if you have to be in this collision. Because the truck is not going to slow down as fast. The car is probably going to turn all the way around in a very short period of time. So, and that's mainly due to the fact that acceleration equals the force divided by the mass, or the sum of the forces divided by the mass. So for the big truck, that's going to be a small acceleration, and in the small car, it's going to be a much larger acceleration because the mass is smaller. Which is actually the next question here. Which vehicle undergoes the greater magnitude acceleration? And the answer to that is D, the car. So just to make this a little bit more complicated, let's say this is acceleration of the car and mass of the car, acceleration of the truck, mass of the truck. And let's talk about the force on the driver, between the driver and the seat belts, because they've got, of course, they're both good drivers wearing seat belts. So the force on the driver of the car is going to be basically mass times the acceleration of the car, because what effects does the driver have on him? Let's make a little force diagram. Basically, he's going to have the normal force pushing up. He's going to have the force of gravity pushing down, and those are basically going to cancel each other because he's not accelerating upward or downward. He is going to be going this way, which is his mass, or his acceleration, and his force is wait, no, actually, I'm wrong. He's going to be pushed by the belt. He's going to have force of belt going this way. And there's not going to be much force between the back of the chair and him because he's being pulled back by the belt, and that's the only force that's going to be acting on him that's not canceled out. And his acceleration is also going to be that way, as he is being slowed down by the belt. And we'll make this statement that the acceleration of the car is equal to the acceleration of the belt. So, which is in turn equal to the force of the collision up here divided by the mass of the car. So, and we'll also use that as the force of the belt over the mass of the mass of the driver of the car. We can also say the acceleration of the truck was the force of the collision divided by the mass of the truck, which is equal to the force of the belt on the truck. This was the belt of the car divided by the mass of the driver of the truck. So if we wanted to know the force of the belt on the car divided by the force of the belt on the truck, we can take some of these things and basically I want to take this term and multiply it over there, take this term and multiply it over there, so I can get a division between the force of the belt on the car divided by the force of the belt on the truck. So I take force of collision over the mass of the car times mass of the driver of the car divided by force of collision over mass of the truck times the mass of the driver of the truck. Some things cancel out there, basically these two. And this is our expression. For the moment, let's imagine that the mass of the driver of the car and the mass of the driver of the truck are the same. And we basically get a situation that the force you're going to be experiencing in that car divided by the force that you're experiencing in that truck is the mass of the truck divided by the mass of the car. So the car driver experiences a larger force by that factor, and the truck driver experiences the smaller force by that factor. And this part means that if you're the driver of the car, or the person who has the larger mass is going to experience more force than the one with the smaller mass. So I just made that quick quiz way more complicated than it needed to be, but I hope it wasn't too painful.